Homework 156, Mr. Gazda here. Watch this. Erosion, streams, and mass movement. So, mass movement is basically erosion by gravity. Think of like rock fall. Rocks breaking off the side of a cliff, falling down, or landslides. Okay? You don't have a lot of movement. You don't have a lot of that abrasion of rocks bouncing into each other. It streams, you do. You have a lot of abrasion, rocks bouncing into each other. And therefore, here you go. Rounded sediments will be... Streams will have those. Unsorted sediments will be A. Mass movement, they all just end up in a pile, big rocks, small rocks. Angular sediments will also be mass movement A. Smooth sediments will be B. Okay, all the abrasion will make those rocks in a stream smoother. And then sorted sediments will be B. When it deposits it, the sizes are going to be very... the size sediment will be sorted. Deposits in layers called beds, that is streams, that leads to sedimentary rock. And then number one erosional source of Earth over the past 50 years, that is streams. Right now, streams cause the most erosion on Earth. May not have been the case back 20,000 years ago. It was glaciers, but we're talking about over the last 50 or 100, 200 years, it is streams. Know those things. Here we go. Here, in a stream, water's fastest on the outside of the curve, and the water slows down on the inside of a curve. On the diagram below, color over the sections of the stream bank that is experiencing erosion with red. So, faster water causes erosion. It will take away the land. Slower water will cause deposition, and you have to be able to figure that out. Therefore, you're going to have erosion on the outside of streams where it's going faster. So, I'm going to color over it with red, and a lot of kids get this wrong. I think they just don't read the question carefully enough, and they just kind of start coloring. Red is going to be the outside of the stream. You kind of see it here even. Outside, water goes faster, and I can even do it here. And then green, sediment, the deposition. When water slows down, sediment in the stream, sediment the stream can no longer move is deposited. Color them green. Where is sediment going to build up? Because it is deposited on the inside. You kind of see it here with the little, they kind of drew it as little dots, meaning sediment's deposited here and here. That's key. Inside of the curve, deposition, because the water's slower. Outside is erosion. That is what you should get. 10. Which sediment will settle at the fastest rate, meaning speed? Which will settle through water fastest? Okay, now you got to look here. There's size, there's shape. This is really flat. Density. Clearly what you want, density, you want denser will go faster, and also larger will go faster, and rounder goes faster. Therefore, of these, the fastest speed will be W. Where's my pen? W. Okay? Which sediment will have the longest settling time? So this is the slower it goes, it takes the more time. So basically, which of these will settle slowest and take the longest to get to the bottom of the same amount of water, 100 feet, let's say? We're looking for kind of the opposite. Low density, and then flatter is going to really slow it down. So that should be that one, Z. If all four sediments were thrown into a lake at the same time, which will reach the bottom last? Same basic idea. Longest settling time, but it will hit the bottom. It will hit the bottom last. Go at the slowest rate. That would be Z of all of those. Okay. Next page. Rivers erode V-shaped valleys. Glaciers erode U-shaped valleys. This is key. On the diagram on the right, color over the V-shaped valley of this river with blue pencil. Cover over the valley. Blue pencil. This is the valley that it erodes. This is a cross section here. That's the V shape of which we're talking about. All right. Okay. Earth Science, page 6 for the following questions. Let's just do a few of these. Okay, so what is the diameter of the largest sediment that can be transported by a river that is flowing 0.5 centimeters per second? So this is reading this graph, and the key thing is the key thing here is this line. Now I want to erase this line that someone drew in here. Okay, so we are looking at rivers flowing 0.5 centimeters per second. So then we kind of follow it up to here as best we can. Okay, and look, it's right on this line, 0.01 centimeter diameter, 0.01 centimeter. And you need to have, so it's 0.01 centimeter. Alright? 15. Ask the question, what is the diameter of the largest sediment that can be transported by a river that is flowing 10 centimeters per second? So, now we are here. How does this look? We're here. 10 centimeters per second. This line tells you what can be transported. Okay? That's what we're interested in. This tells us the data. This line is what this is all about. This is just a scale. So 10 centimeters per second goes up to here. Look at that. It's dead on that line of this. And it's basically 0.2. It says it here. 0.2. 0.2 what? Centimeters. 0.2 centimeters. Okay? And then this you should get using the same chart. I'm trying to save some time. 2.0 centimeters, 17, 1.0 centimeters. And then 18, let's do some of these. True or false? A river flowing 2 centimeters per second can transport pebbles, sand, silt, and clay. 2 centimeters per second. Pebbles, sand, silt, clay. So 2 centimeters per second is right here. Notice the scale kind of changes a little bit, but this is 2. Okay? So it could transport this size and anything below it. So it could transport sand and silt and clay, but can it transport pebbles? Okay, pebbles is this range right here. It cannot transport pebbles. Does it say pebbles? Pebbles. So that will be false. 19. A stream's velocity decreases from 6 centimeters per second to 0.2 centimeters per second. At the new slower rate of water, the stream can no longer transport sand-sized sediment. Alright, so that's kind of a mouthful. Read it again. Read it a third time if you need to. So it's going 6 centimeters per second. For whatever reason, the river then slows down to 0.2 centimeters per second. Can it still transport sand at that 0.2 seconds? So, if it's... Here's an announcement.
Guadalupe Gomez, please come to the main office. Thank you.
So at 6 is here. Okay. So at 6, it can transport sand, silt, and clay, and then it goes down to what, 0.2? I think it says 0.2. It does say 0.2. 0.2 is right here. Okay. Now 0.2, notice, it can transport silt, and the smaller clay can't transport sand. And it says can no longer. So this may get you with the wording, but true. The answer is true. At this new speed, it can no longer transport sand-sized sediment. Alright. 20. Stream flowing cannot transport clay-sized sediment. Okay. 0.05 cannot transport sand. 0.05. 0.05. It can transport silt and clay, so that's got to be false because it can. Okay. 21. How can you tell that sample Y was not deposited by a mass movement such as rockfall? Okay, the main thing here you can tell, well, they are unsorted. Rockfall will be unsorted. The key thing here is that these are rounded. A rockfall of rocks falling off a cliff and falling 100 feet, 200 feet, 50 feet, they're going to be angular. Okay, so sediment, something about the sediments here are rounded, and mass movement will have angular sediments. Okay, the sediments are not angular, or the sediments are rounded. Something like that. Know that. Here we go. I'm going to go a little quicker here. Drainage basin. What's key here is you got to realize drainage basin is the area that the stream will flow into. Okay, let me try to explain this here. I have a thing here. It's a little hard to see, I think. Let me see how this goes. I have this model here. I have this model, okay? Let's see how this works. And you can see, if this is a river right here, right? You see, this is a drainage divide. Water that falls here will go into a river down here, and the water that falls on this side of it will go into this river. They will probably meet up down here somewhere, but... So this is the whole of this particular river right here. This whole area is the drainage basin, okay? And the divide for it is the top of this ridge. I wish I could get this better. It's hard for me to do this by myself. Okay. Drainage basin is all the land that will runoff will drain into a certain stream. So, with that said, let me put this back. Go back to our original setup here. Looking like that. So, okay, so point J. So how is water going to flow for point J? Let's do this kind of quickly. Where's point J? Point J, it's going to flow kind of downhill, perpendicular to these lines. This is downhill. This is you really understanding this. So it's going to flow here. It's going to flow into stream C. Stream C. Point K is going to flow. It flows perpendicular to the line. So the water hits here will kind of go like this, and will end up in stream A, which is 1. Point L is going to, so there's probably like a ridge right there. It's going to go downhill here into stream B. That's 2. Point M is in what drainage basin? Point M is going to go down this way, off the map. Therefore, answer 4. Okay. Drainage divide, watershed. Think of your knuckles. Carefully draw a dashed line for the stream watershed B. No, stream B. Neatness counts. So, stream B is here. So you want to envision where this ridge is that separates the watershed for A versus B. And you see this will flow here. So this is a ridge right here. This is really hard for some people. Okay, it kind of flows like this. And then what it does down here is a little bit weird. Don't worry about here so much. It's really about the top. And then here what we're going to have is something kind of like this. Okay. Carefully draw a dashed line. It should be a dashed line, but this is all the drainage basin for stream B. Again, that is tricky for people. And we're going to draw a solid line. Maybe I'll do it in green. You don't have to do it in green. For stream C. So this is also a little hard. What flows into stream C? Kind of this right here. And this again, it gets a little weird. And it's not a super exact science, but this is all the drainage basin for stream C. So hopefully you can get some of this on the back. Okay, let me just go through the answers here. On the back, this is going to be neither, Maple Stream, Colden, and Maple. And you should be doing this to check your answers. So again, realize that it's going to flow perpendicular to the line. So this is going to flow kind of like this into there. Let's just skip 8 for now. We're going to carefully draw color in the watershed of Maple Stream blue. And I kind of did it here. Something like this. This is where it gets a little weird, but the top of this hill, this is water's going to drain kind of downhill here. This water will drain downhill into Colden Creek. So this is really the watershed for Maple Stream. Hopefully you get the concept of this. Again, this is tricky. And then give a possible elevation of the shoreline of Lake Lackawanna. You got to figure out 10 feet. This is 500, 490, 480, 470. Okay, so it could be 460. It could be anything in the range of 460 to 469 feet. Hopefully you can get that concept as well. Has that feet on there? These are in feet. Be careful. And then what's the highest possible elevation for point S? Point S here. Well, this is what gets people sometimes. Again, it goes by 10. 500. This line is 500. 510, 520, 530. If there was another line, it'd be 540, but it's not. But it's uphill of 530. What's the highest it could be without being 540? Highest possible, 539 feet. Okay, so really the first 2 pages are the most important for sure. The watershed stuff is tricky for people, so but it is a good concept, and make sure you know this. And I'm Mr. Gazda for all the fine folks at Gazdoni Productions. Thanks for watching.